Welcome to The Explainer. Today, we're going to pull back the curtain on something you use every single day but probably never see. It's the invisible architecture that powers every app, every website, every piece of software you rely on. We're talking about data structures.
And look, this isn't just some dry academic topic. As one Google engineer put it, getting this right can make the difference between an okay product and an outstanding one. That's a pretty big deal, right? It's really the key to building exceptional tech.
You know, the real difference between a good programmer and an excellent one often comes down to this: knowing exactly when and how to use the right data structure. So in the next few minutes, we're going to start you on that journey, demystifying the core concepts that all the great developers have absolutely mastered.
All right, let's jump right in. Here's what we've got on tap. We'll cover what data structures are, the difference between the blueprint and the building, how we keep score on efficiency. We'll put an array versus a linked list head-to-head, and finally, talk about choosing the right tool for the job.
All right, first things first. Let's tackle the big question: what are data structures?
You know, when you boil it all down, it's actually pretty simple. A data structure is just a way of organizing data so you can use it efficiently. That's it. It's a specific format for organizing, processing, retrieving, and storing all that information.
Okay, so why should you care? Well, because picking the right structure is what lets you build fast, powerful algorithms. It helps you manage and organize data in a way that just makes sense. And, ultimately, it leads to code that's way cleaner and a heck of a lot easier to understand.
Okay, so now we know what they are. But to really get it, you have to understand this one key idea: the difference between the blueprint for a house and the house itself. On one hand, you have the abstract data type, or ADT. Think of this as the what. It's the concept, the set of rules. For example, a list is an ADT. You should be able to add things to it and remove things from it. Then you have the data structure itself. That's the how. It's the real, concrete tool that actually makes the ADT happen, like an array or a linked list.
Here's a great way to think about it. The abstract goal, the ADT, is just I need a mode of transportation. That's the idea. The concrete solutions, those are your data structures. You could walk, you could bike, you could take a train. See? Each one gets the job done, but they all have different pros and cons depending on what you need, right? How far you're going, how fast you need to get there.
So that leads to the next question. How do you decide between walking, biking, or taking the train? You need a way to measure them, to compare their performance. And in programming, our measurement tool for that is something called Big O notation.
As programmers, we are obsessed with two questions. How much time is this going to take to run? And how much memory or space is it going to eat up?
The easiest way to think about Big O is like a performance scorecard. But here's the key. It doesn't really care about small amounts of data. It's all about the worst-case scenario. It tells us how an algorithm is going to hold up when the amount of data gets huge.
And this chart breaks it down perfectly. You've got these different tiers. O of 1, or a constant time, that's the holy grail. It's super fast, and it always takes the same amount of time no matter what. Then you have O of n, or linear. It's okay. The time it takes grows in a straight line with your input size. But then you get to things like O of n squared, quadratic, and that's a huge red flag. It gets really, really slow, really fast, and you want to avoid it if you're dealing with a lot of data.
Okay, enough theory. Let's make this real. We're going to look at two of the most fundamental data structures out there, both of which are ways to implement that list idea we talked about: the array and the linked list.
So think of an array like a bookshelf, where every slot has a number. If you want the book in slot number 5, you just go straight there. It's instant. A linked list, on the other hand, is more like a treasure hunt. You start at the very first item, and that item contains a clue that points you to the next one, which points to the next, and so on. You have to follow the trail.
And here's where we see their Big O scorecards. For accessing an item by its index, arrays are O of 1, constant time, blazing fast. But if you want to insert something in the middle, whoa, that's O of n. You have to shuffle everything after it down one spot. That's slow. Linked lists are the complete opposite. To find an element, you have to do that treasure hunt. So access is slow, it's O of n. But once you find the spot, inserting or deleting is O of 1. Super fast because you just change a couple of pointers. You don't have to move anything else.
So what's the big takeaway here? Is that there is no best data structure. It's always about trade-offs. This isn't just theory either. Think about your social media feed. If the developers used a structure that was slow for insertions, you'd feel that annoying little lag every single time you pulled a refresh. On the other hand, if they used one that was slow for access, trying to find a post from a year ago would take forever. The choice always depends on the problem you're trying to solve.
And that really brings us to the final and most important point of all this.
So let's recap what we've covered. We've seen that data structures are all about organizing data for efficiency. We know that ADTs are the idea, and the data structures are the actual implementation. We learned that Big O notation is our performance scorecard, and that every single structure has its own unique set of trade-offs.
And this is why it all matters. Knowing how to choose the right tool for the job, understanding those trade-offs, and making a conscious choice, that's what elevates your work from just good to truly great. It's the mark of an expert.
It completely transforms how you approach building software. You stop thinking about just making things work, and you start thinking about making them work brilliantly. So we'll just leave you with this question. Now that you know about the tools, what problem are you going to solve?